So, good morning, guten Morgen, Mitakulu, wie geht's? How are you doing? Any questions so far regarding the lectures of our course Machine Learning Basic Principles? So I said it several times and I say it again, please make heavy use of the exercise garages, where you can ask any questions about exercises or lectures or the course book, anything related to the course, to TAs, or discuss with your colleagues. We also have a Slack online discussion forum where you can post questions and discuss among each other and also ask TAs. Sometimes I also have a look and try to respond. Okay, so let's continue our discussion of drawing apples or machine learning problems that come out or arise within drawing apples. So in the last lecture, we talked about a method for predicting the confidence in that a drawing represents an apple based on features, simple features of a hand drawing. So if the hand drawing is in the form of a 16 times 16 pixel black-white bitmap, we could stack all the pixels, either if they are black or white, into a vector corresponding to the pixel color. So we then came up with a method that determines a predictor map or a hypothesis map, which is parameterized by some weight vector, which takes the feature vector as input and outputs a predicted label, which is hopefully as close as possible to the true label, so to the true confidence that the drawing is an apple. How did we find this mapping, or this hypothesis map, or predictor? What was the basic idea? Yes? Gradient descent. Okay, so that's already very in the detail, but the big picture in machine learning, how do we learn a predictor that allows to predict labels from features? Yes? We define the loss function. And we simply searched for the one predictor which minimizes the loss. So we were able to compute the loss since we assumed that we have labeled data. So we have labeled data and can evaluate the quality of a particular predictor by the empirical risk. Empirical risk is a bit more fancy term for just average loss over the labeled data. Empirical risk of a predictor is, so we denote it calligraphic E, depends on the weight vector, W. Yeah, and this predictor, so we kind of constrained our consideration to a subclass of maps, and this subclass is called the hypothesis space, and we focused on linear maps, so the hypothesis space of linear maps, which are of this form. So they take a feature vector as input and output a linear weighted combination of the individual features, x1 up to xd. Yeah, for those which wonder why I sometimes underline symbols, in my training a long time ago in Vienna, this was used to denote vectors. So on a blackboard, it's difficult to do boldface, to do bold letters, so that's why I use here underline to indicate that this is a vector, this symbol denotes a vector. Also here, the weight vector is a vector. And we can compute the empirical risk over the labeled data just by summing up the loss. So what did we choose for the loss? Squared error loss. So we took the difference of the true label of the ith. So this is the true label of ith data point minus the prediction, the predicted label, which is HW of x I, so this is the predicted label, and we square this difference. Okay? And then we choose the weight vector, or the weight vector which gives the best linear predictor is then the solution of an optimization problem, which we call the empirical risk minimization problem, because we are minimizing the empirical risk. So we minimize over all weight vectors of dimension d. So in order to solve this optimization problem, we need to know the objective function. And again, I highlight, you can only minimize this empirical risk for labeled data points. So you need to have data points where you know the true label, and this might be difficult to get. One question on Slack, on the Slack channel was, when I look at this quick draw app, well, we have this bunch of drawings. So each drawing has a feature vector. This has one feature vector. This drawing has another feature vector. But where do I find this label, which is the confidence in that this drawing is an apple? And this, I didn't look in detail, but this might not be available directly in this form on this quick draw app. But you have to come up with some method to determine the label. What you can do, for example, in order to determine the confidence that this particular drawing here is an apple, you could compute the similarity measure just by taking inner products between the feature vectors of this particular drawing and all other drawings that are known to be apples. And then you might come up with some confidence level between 0 and 1. Yeah, so it's not that easy, and there already the work starts. There already the work starts when you really want to go out and develop an app which evaluates hand drawings of apples. Then you need to think about, okay, here I have tons of data points with feature vectors. I have the feature vectors. So this you can download pretty much directly, this black and white bitmaps. But how do I get the labels for this training data? But for the time being, we assume that we know, somehow we came up with a method to determine the true labels of the training data. This y1 up to yn here. Yeah, if we know the labeled training data points, we can evaluate the objective function of this optimization problem. The objective function is the empirical risk, and minimize it. So how did we minimize this? There was already the comment. Gradient descent. So you can solve using gradient descent. But this is only one way to solve it. This is only one particular way to solve this optimization problem. And now we'll discuss another method, which brings us to the problem of inverting matrices. There were some comments on the first exercise round related to why did we ask you about invertibility issues of matrices. And this now will become clear in the context of linear regression. So if we write down this empirical risk using a matrix and vector notation of the label and features, we end up with inverting matrices when we want to optimize this or solve this empirical risk minimization problem. This goes as follows. So we stack the feature vectors of the training data into a feature, let's call it feature matrix. So first, feature vector of first data point, feature vector of second data point in the training data up to the feature vector of the last data point. And then we transpose it, which is not very important, but will be convenient for notational purposes. So this matrix, what's the dimension of this matrix? So what is the number of rows of this matrix? N. And the number of columns? D. The number of features. And similarly, we stack the labels of the training data points into a vector. So the first label of the first data point, the label of the second data point, and so on till the label of the last data point. So this is a vector of length n. Number of data points, so n, the symbol n throughout the course is always has the same meaning. It's the number of data points in the training set. It's also sometimes called sample size. Sample size. Is it good to have more sample size, a larger sample size, or a smaller sample size? Depends on the resources. Can you explain more detail what you mean? Yeah. Exactly. So there are two contradicting aspects here for statistical purposes. So regarding the ability to learn a good predictor, we want to have as much sample size or as much training data as possible. On the other hand, we need to be able to use this training data. So the larger the sample size, the more computational power we need to really make optimal use of the data. And the larger the sample size, the more labeled data points you need. So the more labeling you need. And labeling costs money. Remember, I showed you the website of the Mechanical Turk. For more labeling, you have to pay more. So more sample size costs more, but also provides more. More ability to predict well. Yeah, so if we define this feature matrix and this label vector, then we can rewrite the empirical risk here in linear regression as follows. As the squared norm of the difference between the label vector and x feature matrix times the weight vector. So the optimization problem, or the optimal weight vector, which is defined as the weight vector which minimizes the empirical risk, is obtained as the optimizer of this optimization problem here, which involves the squared norm. Can we solve this? So this y and x is fixed, is given. This is given. Once we have the training data set, we determine, we evaluate the features, stack them into the matrix X, we get the labels, stack them into the vector Y. So Y and X are given, we optimize with respect, we tune this quantity with respect to W, the weight vector. Does anybody know how to solve such an optimization problem? Yes? Yes. So if we denote this term here, this objective function, as fw, then the optimum is characterized by the zero gradient condition. Which means that the gradient of this objective function at the optimal weight vector has to be zero, the zero vector. So now we plug in the particular expression for this objective function. What is the gradient of this function? Well, you can look it up. I have shared a link to the matrix cookbook. You might have a look at this matrix cookbook, which collects some basic identities for taking derivatives. It turns out that the gradient of this function is minus x transposed, here with factor 2, times y minus x, the optimal weight vector, equals to 0. Okay? Did I forget something? Did I make an error? Yeah, as I said, you can look this up, how to take the derivative or the gradient of this expression at the matrix cookbook. So, but this equation characterizes the optimal weight vector. Once we solve this equation, we get the optimal weight vector. We can plug it into our expression for the linear predictor, and we get an optimal predictor, a linear predictor, which takes the features of the drawing as input and outputs a predicted label y hat, which is as close as possible in terms of the squared error loss to the true label y. How many of you would say they know how to solve such a linear equation? Yes, some. So please tell me what's the solution. Yeah, so this is pretty much straightforward using linear algebra. It turns out that this is equivalent, so this condition is equivalent to x transposed y equals x transposed x w optimal. So now I have kind of applied a bit massage to this equation. I'm now at this equation, which characterizes the optimal weight vector. Not right there. So I only want to have this weight vector w opt on one side. So what is the final step here? Yes? Multiply from the left by xtx inverse xty equals optimal weight vector. So here pops up the inverse, which we asked you about in the first quiz. So you can solve this linear regression problem directly without any gradient descent iteration, which only gives you a kind of a sequence. So remember, gradient descent gives you a sequence of vectors which become more and more close to w, to the optimal weight vector. However, exactly, they reach it never exactly. It becomes more and more close. So gradient descent gives you less. It gives you a sequence of weight vectors which are more and more improving or an increasingly more accurate approximation of the optimal weight vector. This approach gives you the exact weight vector, which is the optimal. So why should we ever use gradient descent? Exactly. This here, I can write it down easily. So how do you compute the inverse? Well, maybe it's not invertible. So this works if xtx is invertible. So this equivalence doesn't hold in general. This equivalence only holds when this matrix product is invertible. Moreover, if it's invertible, how difficult is it, or how do you compute the inverse? I mean, I can now write this down easily on paper on the iPad. But then when I have actually tons of feature vectors, stack them into a matrix X, so I have a big, big matrix, millions by millions of elements, how do I compute the inverse? I don't accept the answer using MATLAB. There's always this joke for mathematicians, how do you compute the inverse? Using the MATLAB command pinf, pseudo-inverse. So this is not allowed here. Yeah? So in linear algebra, people came up with clever ways to compute the inverse. would you say it's kind of efficient and can be done fast for big matrices? No. So you don't want to invert big matrices without knowing more about the matrix. So if you know more about the matrix, if it has a special structure, for example, it has only non-zeros on the diagonal, then okay. But a general big matrix, you don't want to invert. And this is topic of current research. What is the most efficient way, or what are most efficient methods to invert such big matrices? And it turns out that the difficulty in computing this inverse depends heavily on the condition number of this matrix. So the condition number is the ratio of the largest eigenvalue to the smallest eigenvalue of the matrix. And if this is large, this condition number, then it's difficult to invert the matrix. If it's small or close to 0, then we are happy. If it's close to 1, condition number is always larger or equal to 1, and if it's close to 1, then we can invert it easily. But if it's large, we cannot invert it easily. Do we have control over the condition number? Can we tune the condition number of the feature matrix here? Anybody with an educated guess? Yeah. This was a good guess? No. The feature matrix comes from the data. So the feature matrix is made up from the feature vectors coming from these black and white images. I have no control what the properties are of this matrix. I have to take whatever I get. This might be noisy features, might be manipulated features, might be anything. So this matrix here, this matrix X could be identically 0 because some sensor or some measurement device failed. So I have no control over this matrix X. That's why this approach is rarely used in practice. It looks nice on a paper because you can write down a closed form expression for the optimal weight vector, but computing or evaluating this closed form expression is often much more difficult than the simple gradient descent, repeating the simple gradient descent update steps. However, for a large number of iterations, but each iteration is simple. And there's also a way to speed up the iteration itself using stochastic gradient descent, for example. So is it now a bit more clear why we are concerned with matrix inversions in machine learning? Having a good understanding of how difficult it is to invert a matrix allows you to decide, do I solve this empirical risk minimization problem using gradient descent, or is it worth to go for this closed form solution? Because if you somehow know more about the data, if you spend tens of years using this quick draw data set and you found out that the condition number might be close to 1, then you can go for this solution. But the first shot is typically using gradient descent because it's so robust. Gradient descent works if this feature matrix, if this matrix here is non-invertible, it works also then. And it works also well if this is not well conditioned, so if the condition number is larger, significantly larger than 1. So gradient descent is kind of the robust, simple to use, off-the-shelf method to do linear regression or to solve this optimization problem arising within linear regression. Yes? Will these notes be available in my courses, these hand drawings? Yes. So I put the hand drawings of the previous lecture also there. Did anybody not find them, which was looking for them? Yeah, I will put this on my courses. Okay. Any other question regarding linear regression, gradient descent, linear algebra? Okay, then let's move on to a similar but related task which is given a hand drawing, today I use color, given a hand drawing of an apple, decide, or given a hand drawing, decide if this hand drawing represents an apple or not. So this is now a classification problem. What is the label for this application? So we want to now develop an app which does not go for predicting confidence that a hand drawing is an apple, but which just goes for categorizing hand drawings into representing an apple or representing no apple. So what could be the label here? 0. Yeah. So I like -1 more. So we could say why the label is -1 if the drawing is no apple. Or we could say y is +1 if the drawing shows an apple. I can use any two different numbers. I can use 0 for no apple. I could use 10 for apple. I just need to use two different numbers, and for some reason using -1 and +1 yields nicer looking expressions in the end. But you can, without any difficulty, translate all the expressions that we derived today, or which you find in the course book, also translate to the encoding 0 for no apple and +1 for apple. But we here use the encoding -1 for no apple and +1 for apple. And as features, what could we use as features? Well, the same as before. We could use the pixel values of a 16 by 16 bitmap. Maybe now we use colors. We could use the red component and the green component. But for the sake of exposition, let's assume we have only two features. We came up with two relevant features, x1 and x2. We will see how we can automatically learn good features in a later exercise round, which is about feature learning. But today, we assume that some feature engineer, we had somebody in our company which is a feature engineer, and he found out, or she found out, two very represent numbers, which can be computed easily from the pixels of the hand drawing. What is the feature space here? This here, no? So we have two real numbered features, gives feature space r to the power of 2. What is the label space here? -1, 1. Okay, what do we need more to specify a machine learning problem? Or what does a machine learning problem include otherwise? We have now a feature space, the set of possible values that the features can take on. I can measure the features of a hand drawing, and I want to know the label. So how do I get from the features to the label? I need a hypothesis. I need a map from features to the labels. So here we have label, which is an element which takes on a value from the features label space. We need a hypothesis, and when the label space is discrete, we call this hypothesis. We use a different name also for this hypothesis map. Yes? Yes, x1 and x2 are real numbers. For example, x1 is 10.3, x2 might be 0.1. Real numbers, those two. So a hypothesis map, and for discrete label spaces, we call this also a classifier, which takes the feature vector as input and outputs a predicted label, which is also either -1 or 1. And we want to choose a classifier such that the predicted label, y hat, is a good approximation to the true underlying label, y. How can we implement such a classifier which takes a feature vector and outputs a label, -1 or +1? How can you implement such a classifier? No, the loss function you use to evaluate the quality of a particular classifier. But so far, we first need to find out how do we implement the classifier. How do you do it in reality? I mean, I now write a lot of math, but how do you turn this into an app? So how do you implement the classifier? Sorry? There are algorithms, so you use a programming language. Again, you can implement a particular classifier using a MATLAB code, function, classify, drawing, which takes as input drawing, does some computation, and outputs a predicted label, return y hat. So, and the question is, what do we do here? What do we do here? How do we design such a classifier which reads in a drawing, for example, a red, green, blue bitmap, or we found out that there are two good features, so that it reads in these two numbers, x1 and x2, and outputs a guess or a result of a classification result, either -1 or 1. So how do we do this? Yes? So we already assume that we get the input as a feature vector. So you get the feature vector, and then you would, what did you suggest? No, you don't know the true label. You get the feature vector of a new drawing where you don't know if this is an apple or not an apple. So how do we implement this, or how do we design this classifier? In the old days, or the non-machine learning way would be to try to find out, for example, is there a lot of red in the drawing? What is the proportion of red pixels to green pixels? So yes? Yeah, I could say y hat is weight vector times feature vector. So a linear predictor, a linear classifier. This will be the way we go. But for now, I want just to highlight a non-machine learning way to design such an app or such a classifier would be to come up with tailor-made rules, kind of analyze the hand drawing, how many red pixels are there, how many green pixels are there, then do some maybe if clauses here, if else. This is the non-machine learning way. And the machine learning way, what is the machine learning way to design a good classifier? Yes? Use a weight vector, kind of use a parameter. For each value of the parameter, we get a different classifier. So we have a hypothesis space, which is a set, a bunch of different classifiers. So here we have one, which is weight vector 1. Here we have another one. Weight vector 2 is another classifier. So we consider a big set of different classifiers. You can think of each classifier being another function, being the source code of another function. You try out all those different classifiers and pick the one which is best. That's the machine learning approach. So how do we specify these functions or these classifiers? There was one suggestion, well, let's use this inner product. So we take a classifier as classifier a linear map. We read in the feature vector, compute the inner product with a weight vector, and this is our predicted label. Okay. This seems natural because we did exactly this in linear regression. Okay. Is this good here for classification? Yes? Yes. Yeah, so the comment was we need a border or somehow classify between the two classes, because this here is a real number. This can be any real number. An arbitrary real number can be 10, can be -1. However, the label is either +1 or -1. So what we can do, we can say, we do not use this for the final classification, but we make a thresholding step afterwards. We say the predicted label is -1 if this map here yields a negative value, or smaller or equal than 0, or +1 if this yields a larger value. Okay. We can, or it's not very intuitive, or it doesn't look very promising to use this map. In principle, we could use this map to predict or classify the drawing. However, we do not take in any way into account that the label, which we're interested in, takes only values -1 or +1. And that's why we do not use this directly, but we add a thresholding step. So we first compute this predictor map, and then threshold at 0. And how does this look like in the feature space? That's why I came up with a two-dimensional feature space, because I can draw it easily. So let's say we have a particular drawing, some drawing, which has a feature vector x being here. So this drawing has a certain feature vector, let's call this x1, which is here. And what this rule here does, this classifier, it kind of divides the feature space into two half spaces, where in one half space we say y hat is equal to 1, and in the other half space we say y hat is equal to -1. And it turns out that the boundary between these two half spaces, which we also call decision boundary, this is a decision boundary, it separates two parts of the feature space which correspond to different classification results. So in one part, we say if the feature vector is in this part, we say y hat is 1. So we would predict the label for this data point here as y hat 1 equals 1. And in the other part, we would say the label would be -1. And these two components of the feature space are separated by a decision boundary. And it turns out this decision boundary is closely related to this weight vector, which we use in this predictor here. In particular, this weight vector is a normal vector to this decision boundary. So this is nothing. What I have shown here is the representation of what the effect is of this classifier in the feature space. So this here, this plane which I used here, represents the feature space, all possible feature vectors. Yes? So the question was, what do you do if you have a feature vector which is, for example, exactly here on the decision boundary? So we have a third data point with feature vector x3. So this depends on how we define the classifier. In this case, I use the equal 0 here for -1. but typically this is not very important, where you put the equal sign, here or here. Because the probability, if you have a probabilistic model, the probability that you hit the decision boundary is basically 0, which does not mean that it never happens, but it's typically not affecting or relevant for the overall performance of the machine learning method. Okay, so let's not consider this special case of having a data point directly on the decision boundary, but having data points. So let's say we have here another data point, x4, on either of the two sides of this decision boundary. Okay, so the hypothesis space now is characterized by the set of all functions, of all linear functions. And this is exactly the same hypothesis space as we had for linear regression. So we now consider a classification method, which is called logistic regression, which uses the same hypothesis space as linear regression. However, what is the difference? It uses another loss function. So let's now look at the loss function. How do we measure the quality of a particular hypothesis? So a particular hypothesis or classifier is given by this expression involving a particular weight vector. So a particular weight vector defines a particular classifier as the weight vector here defines the decision boundary. But how good is a particular classifier or predictor HW here? How can we measure the quality of a predictor? Yes? Okay. So this distance, we want to make this distance as large as possible from the decision boundary to the points. Yes, that's one way. However, it's difficult to read out the loss function from this. So there's a particular loss function which does exactly this, which is called the Heinz loss, but which we will not discuss today. But intuitively, we should choose this W, this weight vector, such that in this feature space picture, the data points of the two classes are as far as possible away from the decision boundary. And this distance to the decision boundary is sometimes called margin. So maximum margin methods try to find a weight vector W, which makes this margin, the distance between the decision boundary and the labeled data points, as large as possible. Okay, but let's now try to come up with another loss function. What loss functions are there? What could we use? So remember, a loss function tells us if we have a particular data point, let's say we have this data point 1, the first data point here. Let's say we have a data point data point 1, which has feature vector x1 and which has a true label y1, which is, what do you guess? Do we know the true label of this drawing? What could it be? Could be an apple, no? +1. Yeah. Let's say the true label of this apple is +1. So, and now we need a loss. Let's say we have a particular classifier with a weight vector W, and we apply it to this data point with feature vector x1 and true label y1, which is +1. How do we measure the quality of this predictor, this classifier? So let's draw this in a diagram where we show here the value of the predictor and here the loss. Let's now design a loss function. You can design loss functions. You can take whatever loss function you like in principle. So if we apply it to a data point with feature vector x1 and true label being +1, and the value is positive, so here it goes to +infinity. what do we want to have for the loss function? How should the loss function behave in this direction here? Should it go up? Should it go down? So the true label is +1. So it should be on this side. And the value of the predictor basically tells you the distance to the decision boundary. So this here, the value of the predictor gives you an idea of how far away this x, this particular feature vector, is from the decision boundary. So for large values, we are on the right side. So the sign of the predictor, the sign tells you on which side you are. So here the sign is positive. HWX is larger than 0. On this side, the predictor is negative. So now we have a data point. We have a data point which is on this side, y equals +1. Y equals +1. And let's say we have a weight vector which defines the normal of the decision boundary such that the feature vector gives a high positive number. So we are on the right side and we have a high positive, we also have a large magnitude of the predictor. Is this good or bad? So we are on the right side of the decision boundary and we are very much so on the right side. So should the loss be large or small? Small, it should go down, yeah? Let's look at the other side, at the other extreme. Let's say we still consider the same data point. So the true label is +1. However, the predictor tells us we are on the wrong side. And let's say it's very much negative. So we are very much on the negative side. So we would have this case. The data point would be here. So the true label is +1, which would mean we should be on the other side, but we are now on the wrong side. And the value of the predictor is very large in magnitude. So we are very much in the wrong half. So the loss function of this wrong decision, of this very much wrong decision, should be very large, should go up. So, and basically we have it. Our template for a loss function that we would like to have for a classifier. Here in the middle, what should we do in the middle? Somehow connect these two parts, but the basic behavior is defined. For very much positive or very large positive values of the predictor, the loss function should go to 0. For very largely negative values, the loss function, when applied to a data point with label +1, should go to infinity, should go large. Do you know a loss function which does this job? Which loss functions do this job? Having on the left side this asymptotics to +infinity, and on the right side go down to 0. Can we use the squared error loss for this? So we know already the squared error loss. Squared error loss would be, we just take the predicted value minus the true label. So we use this for the first data point and square it. So how does this look like in this figure? It looks like this. So we have, so if this is +1, so we have +1, it goes to 0, and here it goes like a bowl. So this is the squared error loss. Does this make sense to use the squared error loss here for classification? Nope. Sorry, what was the question? You can use? You mean as a loss function, some exponential, some kind of exponential function? So squared error loss, no good for classification because it does not fit the bill. Either on this side, it does not go to 0, or on that side, it doesn't go, on one of those two sides, it does not go to 0. It always asymptotes to plus infinity. That is what we do not want for classification problems. Because on one side, we have kind of positive or correct decisions, and the distance or how far we are to the right tells us how much confidence we have in the positive decision. And these very much positive decisions are always penalized if you use the squared error loss. Another option, which is related to the suggestion of the student, which said exponential functions, it turns out that using not directly the exponential function, but somewhat related, which is the logistic loss, which is log of 1 plus e to the power of minus hwx. This loss function looks like this, and it fits the bill. So on the left, it asymptotes to infinity, and on the right, it decays to 0. So this is the logistic loss. Are there other choices for loss functions? Well, I told you one possible choice is also the 0-1 loss, which is 1 and 0 on the right. So this is the 0-1 loss. The 0-1 loss has kind of the particular property of being, in some sense, an approximation of the error probability. So if you use the 0-1 loss and minimize the 0-1 loss averaged over a large number of training samples, then what you minimize is an error probability. So from a statistical perspective, the 0-1 loss is kind of the optimal loss, but only from a statistical perspective. Why do you think we do not use the 0-1 loss often in practice? Yes? Yeah, it's non-differentiable and non-convex. It's difficult to optimize. It's difficult to kind of guide choosing the weight vector W using the 0-1 loss. We cannot use gradient descent for the 0-1 loss. What is a typical strategy to cope with non-convexity? So if you have a function which is non-convex, how can you get rid of this non-convexity? Are there any mathematicians here? What do? You have a non-convex function, you do not want to work with non-convex functions? Hinge loss. You approximate it by a convex function, and you approximate it by the convex function, which is kind of the tightest approximation. And in this case, it turns out you can find an upper bound, the convex upper bound, the smallest convex upper bound on the 0-1 loss is called the Hinge loss. And using Hinge loss yields another family of classification methods, which is called support vector machines. I will not go over support vector machines in this course. You can find more details in the course book, and they are also discussed in more detail in follow-up course on kernel methods. So we have now 3 loss functions which seem reasonable for classification. The Hinge loss, which is convex. So this is a convex loss function. Is this good? Exactly. We have still the problem of being not differentiable. Here we have a corner point. So you cannot use gradient descent methods. However, the logistic loss is differentiable and convex. And this allows us to use gradient descent in pretty much the same manner as we used gradient descent to minimize the empirical risk problem of of logistic regression, we just plug in a different loss function here and do the same gradient descent update steps. And the resulting classification method is called logistic regression. So logistic regression is based on the combination of logistic loss, using logistic loss to evaluate a predictor, and using linear predictors. Linear predictors of the form weight vector times feature vector. And these linear predictors are then used for classification as follows. Classify as y hat equals -1 if the predictor is smaller or equal than 0, or +1 if the predictor is larger than 0. Okay. So you apply then this predictor to do a classification by looking at the sign of the predictor. So when you do the classification in the end, when you read in the drawing and then classify it apple or no apple, you just look at the sign of the predictor here, of the linear predictor. However, when you train the classifier, when you tune the weight vector, so we want to find, again, we aim at finding an optimal weight vector by minimizing an empirical risk, which depends on the weight vector. And in this case, the empirical risk is given by the logistic loss. Okay. Once you have this optimal weight vector or an approximation to this optimal weight vector, you plug it into this decision rule here, or classification rule. Any questions so far? Yes?
We use the term regression here, so is the regression part just finding the
yeah.
hypothesis that's actually
Yeah, yeah. Well, yeah. Yeah, so the question was, why is it called logistic regression? It's because as a side product of finding this final classifier, we find a predictor which is, in some sense, measures the confidence in the classification. So we measure the reliability or the confidence in a classification, and this is a number. And as I told you in the beginning, these terms regression and classification do not overemphasize too much, because the distinction between regression and classification is very blurry. In the end, we are interested in a map from features to labels. And in logistic regression, we do this using first a linear map and then looking at the sign of the result of this linear map for the classification. And for learning this linear map, a good linear map, so for finding a good weight vector, W, we minimize the empirical risk. It's again empirical risk minimization. Exactly the same manner as for linear regression, but here we use another loss. In linear regression, we use the squared error loss, and for logistic regression, we use the logistic loss. Yes? So the question was, why do we use the log here and not directly an exponential? The thing is that although in principle we want to penalize more if the decision is very incorrect, but there's a limit. So if you would use the exponential, this would grow so fast that one single misclassified data point on this side, which we call outliers, would kind of dominate the final classifier that you learn. So if you have very large fast-growing loss functions here, like the exponential, then the overall method will be very sensitive to singular data points which are not representative for all. And these are called outliers. And it turns out that the best compromise is actually the Heinz loss, because it has slope 1 on this side, And this is optimal regarding robustness to outliers. However, as I said, the Heinz loss has the drawback of being non-differentiable. And logistic loss is convex and differentiable, so we can directly apply gradient descent, so you even can take your code that you implemented for linear regression, the gradient descent iterations for linear regression, and just have to replace one piece. In particular, you have to replace the piece where you compute the gradient of the empirical risk. This looks different for logistic regression. But other than that, the code looks completely the same. So it's very convenient to use logistic regression because you can reuse a lot of methods from linear regression. Any other question? Yeah.
So how does this work when you have more?
So the question was, how does this work when we have more than two labels? For example, when we have three categories. So y might be -1 if finish apple, drawing shows an finish apple, 0 if no apple, and 1 if drawing shows an Austrian apple. But they taste very similar, by the way. So this is a multi-class problem. Here we have three classes. And one standard way to do this is to break this into binary subproblems. So break this into the problem of a binary classification problem where you transform these labels into new label, which is -1 if finish apple and +1 if not. So if either no apple or Austrian apple. Then there is another subproblem, binary classification subproblem, which is -1 if no apple or +1 if apple, either Finnish or Austrian. And then there is a third subproblem, which is a third binary classification subproblem, -1 if Austrian apple and +1 if not an Austrian apple, so no apple or Finnish apple. And for each of these three classification subproblems, you learn, using logistic regression, for example, a classifier, W1, W2, which is characterized by the weight vectors, W1, W2, and W3. And when then there comes a new data point in with feature vector x, you do the following. You evaluate the three predictors for the three subproblems and go for the one which has the largest magnitude, where you are most reliable in the decision, either positive or negative. So you pick the one which has, let's say this yields value 10, this yields 1, and this yields -1. So you then choose the one with largest magnitude, look at the subproblem, and then see if it's a Finnish apple or not. And then combining those three subproblems allows you to determine if it's a Finnish apple, an Austrian apple, or no apple. So this is a very simple strategy. It's called one versus the rest, for obvious reasons. So this way you can reduce a multi-class problem with more than two classes to a sequence or to a set of binary classification problems with only two classes. That's pretty trivial. Yeah. So the question was, how do we get a 10 here? So remember, these are the predictor results. These are not the final decisions. So this is before we do the final classification using the sign. So you need to use the predictor values to find out which of the subproblems is the dominant one. Okay, any other questions?
I'm a little bit confused about the expression in the logistic loss, because
Very good point. So the concern was, why is there no true label? Where's the true label? Well, all what I told here applies for true label being +1. So you can make this applies generally if you insert here a y. Then it applies to data points with some label y, which is either +1 or -1. But this expression then, for example, only works if the labels are encoded as -1 and +1. So when the labels are encoded as 0 and 1, like as in the next week's exercise by our TAs prepared, it's not encoded as -1 and 1, but as 0 and 1. And then this expression doesn't apply anymore. Any other question? Okay, I would say we have then 10 minutes break, and I continue then with explaining how to do gradient descent for logistic regression. Hello.
It's interesting as usual. I have two questions. One of them is that if you said that if gradient descent works anyway for also for the second equation, even that is even either that is invertible or is not invertible, but gradient descent works for it. So why don't we bother with trying a non-gradient descent method?
If you have a computer, if you have a software where you can invert this matrix super fast, then it's faster.
Okay.
Or even if you know more structure that you can invert this matrix by hand,
Alright.
then you have it on paper, the solution. And gradient descent only gives you a sequence of progressively better approximations to the optimal gradient. So it might take longer.
Right. Okay, that's why you might prefer.
Yeah.
Okay. Then I'm not sure if because I thought that last time you mentioned that the feature vector is like 16 by 16, but this time you said it's 1 and 2.
Yeah, I said we came up with two features which are most representative. So some engineer knew how to transform this 16 by 16 pixels into two.
Dimensionality reduction?
Yes, for example, PCA.
So that was just an example. Right?
Yes.
So, like, I'm just wondering how would the betas that look like? So if this whole thing is just for one picture,
Yeah.
and then we are gonna have like green and red, something that represents this pixel intensity of the colors.
So one row would be one drawing. One row corresponds to one drawing.
Okay,
And
alright.
somehow you did a linear combination, or you selected a few pixels
Yeah.
which make up this value and this value. But I don't talk at all about how you come up with these two values. We will see then in the feature learning round how you can find a map from all the pixels to the two most relevant features, which is called PCA, Principal Component Analysis.
Okay, right, yes. Because I was thinking if that is representative of this coordinates is not.
No.
It's just features that
It's
are
highly abstract.
extracted. Yes. Okay. So and then this will be just one picture, and then we will have the next picture and the next picture, just like so.
Yeah.
Okay, thank you so much.
You're welcome.
Okay.
Hey.
Could I ask a question
Yes.
of what weight vector is? I don't kind of understand exactly the concept.
So the weight vector represents the map.
The map, the hypothesis.
The map, yeah. It's just used. We need to represent a map which takes a feature vector as input and outputs a number. And if we restrict ourselves to linear functions, then we can represent any linear function using this with some weight vector.
Oh, so it's a
Just
coefficient.
a coefficient, yeah.
Okay.
Just a coefficient. A coefficient of how much one particular feature goes into the final result.
All right.
Yeah.
And this is 0, right? In the notation.
Yeah, this is 0. It's not 5.
Okay. One more question. I am a bit like familiar with linear algebra. I
Yeah.
studied at business school and
Yeah.
I haven't done algebra for like a few years now, so where could I go myself and learn these basic concepts?
Did you see the announcement? I sent out the link to this matrix cookbook.
Yes.
And then there at Auto you can Google linear algebra courses. But I would say the teacher of linear algebra is Gilbert Strain from MIT. He has open course material
Yes.
which you can download.
Linear algebra.
Linear algebra.
Okay.
Yeah. But so the first exercise gives you a good idea of what we will use. Not much more linear algebra.
All right.
Yeah. So don't worry.
Okay. Thank
Yeah.
you.
You're welcome.
If you were a student and you're taking this minor machine learning and data science,
Yeah.
which courses would you take? Because I have the courses like here. This is like the minor, the available courses.
Yeah.
And I'm taking this as a compulsory course. But I was just wondering if you could tell me which of these are most important. Because I just want to like generally learn machine learning and not go too deep. So what would, because I'm actually, honestly, I'm taking this Bayesian analysis as well right now, because it seems like it's a prerequisite for some other courses here.
Yeah.
So if I were to take 20 credits, what would you take?
20 credits from those.
Yes. You can use it.
This kernel methods, algorithmic methods, Bayesian data analysis you do already,
Yeah.
and deep learning.
Okay.
Yeah.
So
This covers pretty much similar stuff as Bayesian data analysis.
Yeah.
So this might be something you could
leave out.
Leave out,
Okay,
yeah.
that's good because I originally had this in my study plan.
Yeah.
So,
Yeah.
okay, that's
Yeah.
interesting. So you value this kernel
method, yes.
over this advanced probabilistic methods right now.
From the what I know from the contents,
Yeah.
I think this is pretty much covered also in Bayesian data analysis. It's probabilistic machine learning.
Okay.
Yeah.
So this
Just a second.
and how about these are then a little bit more specific. Okay, thank you very much.
So, linear regression method, we get the confidence whether it's how much percentage is right? Like it's 0.85% confidence, 85% confidence that it's enough.
Yeah.
So why can't we just use that as for classification? Like if it's more than 85% confidence that it's enough, it is enough. Or we don't have to do all these other methods. We can just apply the linear regression and use a particular boundary. Like if it's greater than 20%, then it's enough.
Good point. This would work. Yeah, this works if we have labeled data with the confidence level. The data. And for this method, we only have to know it. Good point. Good point. Thank you.
Right now, I just need to do very well, so that is what I'm getting about this.
Let me try it.
So that I have to do that. That I should prioritize. I mean, I haven't been able to read all of the narrative.
Yeah, it's typically just try out the take into account the highest grade of all attempts, and there is no minimum requirement for anyone. So you can just now collect more points in the trial. You cannot do that. So, welcome back to our endeavor of classification methods. Our goal was to find a method to classify a hand drawing according to the categories apple or no apple. And we came up with logistic regression to solve this, or to find a method for constructing a classifier efficiently. I just was asked by one student, why can't we just use our previous app, which delivered us a confidence that a certain drawing represents an apple. So why can't we use the method which I discussed about the last Friday, which is based on linear regression, and enabled us to compute or to predict the label of a drawing, which is the confidence that the drawing represents an apple. So we predict the confidence. If it's more than 50%, we say the drawing is an apple, and if it's less than 50%, we say the drawing is no apple. It's not an apple drawing. Why can't we just use this? Well, we can do the classification using the method that we developed last week, and then just threshold. At 50% confidence, we say it's an apple. So y larger or equal than 50% apple, and otherwise smaller than 50% no apple. Well, the problem is, or the difference is between these two approaches, for linear regression, we needed labeled data with labels being the confidence values. And this is something you do not get directly from quick draw, as I told you in the beginning of the lecture. So to do this, we need reliable information of the confidence that the drawings are apples for many, many drawings. And these we typically don't get easily. In contrast, the approach that I just explained using logistic regression uses labels which are either -1 or +1, either shows an apple or shows no apple. And this is what we get from quick draw. This is what we get from quick draw. We get a lot of data points where we know the label is +1 because the drawing is an apple. We just take this one here. How do we get labels? How do we get data points with the other label, -1? So these are all data points, labeled data points, where we know y is +1. It's typically good to have also data points from the other label, yeah? This randomized set? Randomized drawings, or just any other drawing of no apple, like of a clock. Ideally, a mixture of all drawings, of the drawings for all concepts different from apple. Okay, so using logistic regression, we can directly download the dataset and move along. In particular, we can use gradient descent, as I will now explain, to train or to learn a good predictor. So logistic regression amounts to finding a good weight vector which minimizes the empirical risk, which is the average loss over labeled training data points. So here we said we had 2 features, so the dimension of the weight vector is also 2. And we just add the loss over the labeled data points. So this is the ith data point, corresponding, for example, to the ith drawing in the quick draw database. And now we insert the logistic loss. So So this was log 1 plus e y I times w transposed xi. And here's a minus. So this here is the logistic loss. Logistic loss obtained for the ith data point in the training set. Obtained for ith data point. So, and it turns out that this function here, let's call it f of w, is, guess what? Convex and differentiable. So how do we find the minimum? How can we find the minimum? Yes? Gradient descent, yes. Exactly. So we start with some initial guess, maybe randomly chosen, maybe all 0. So this is the initial guess. And then we update. So we get the new guess by taking the old guess and going into the negative gradient direction. What is the gradient here? So this you can work out using the matrix cookbook, for example. So it's again a sum. And then inner derivative 1 plus e to the power of minus y I w transposed xi times, no, this is the outer derivative, times inner derivative, which is e to the power of minus yi xi times minus yi. Yeah, is this correct? Is this the gradient? Yeah. We could put the summation inside of a logarithm and get a product. Yeah, but I'm not sure if this would help. But in this case, here we are still missing a feature vector, xi. And it turns out that this is very similar form to gradient descent for linear regression. So we have the update is a weighted sum of all feature vectors, and the weight is kind of an error term. Weight EI, this is an error term which measures the error in using the predictor, the current predictor. Okay, so here is WK minus 1. Ah, that's nice. WK minus 1, the predictor from the previous iteration, transposed. So you have this derivation in detail in the course book. No worries if you cannot fully understand my drawing here, but you have it in the course book anyway. So this term here is a weight which weights the feature vectors. So again, we have a weighted sum of feature vectors in order to update the previous guess for the weight vector. Very similar to gradient descent for linear regression. As for linear regression, it is crucial to choose alpha not too large or too small. Because if the step size, so this is called the step size, gradient step size, is too small, we need tons of iterations, and each iteration might involve summing a lot of data points, like billions of data points. N might be billions. Again. So if alpha is too small, we need too many iterations. We cannot afford this. If alpha is too large, then this might not converge, this gradient descent, but diverge up here. Not go to the, so this is alpha too large. There are certain rules or methods to find sufficient step sizes. I have discussed one particular choice for alpha in the course book, so you might have a look at this. And I think in one of the exercises, following exercises, we ask you to try out different step sizes for a particular data set, so you get a feeling for how you can influence the behavior of gradient descent using this step size parameter. Yeah, and we can play the same trick as for linear regression and just randomly sample certain components out of this sum to do stochastic gradient descent. Yes? Yeah, you can get rid of this exponential if you multiply denominator and numerator with an exponential. So I think it's equivalent. Yeah, you might massage this fraction more to have a more compact representation. Okay, so that was I wanted to say about logistic regression. It amounts to a particular combination of loss function, particularly the logistic loss function, and the linear hypothesis space, or the hypothesis space constituted by linear maps. It's the same hypothesis space as we used for linear regression, and the same hypothesis space is also used, for example, for support vector machines. So also support vector machines aim at finding such a hyperplane, such a decision boundary, which is a hyperplane, to separate the two classes as good as possible. However, the difference between the support vector machine and logistic regression is the measure, how they measure the quality of a particular decision boundary. The advantage of using logistic regression is that we can use gradient descent again. So that we can find a convenient iterative algorithm to implement logistic regression. Any questions? Okay, then on Friday you will hear from Timo Hutanen more about the data analysis project. You have now almost all tools at hand to start working on our data analysis project. Okay, thanks a lot.